be auctioning off the real good stuff, ToorCon badges, ToorCon Seattle golden tickets. If you don't have one, you're not getting in. And a bunch of other NSA stuff, but as promised here, an NSA Stein. Do I hear, wow, $20 from Strom in the front. Do I hear 25? 25, do I hear 30? 30, do I hear 35? 30, no, 35, do I hear 40? 35, going once, is that, oh, 40, do I hear 45? 40, going once? 45, do I hear 50? 50, do I hear 50? 50, do I hear 55? Nope, he's at 50. 50 for the NSA Stein, going once, going twice, sold for $50 back there. Give him a round of applause. We'll have more stuff later. Druid, take it away. Thank you. Sorry. Sticker. NSA sticker, $5. Do I hear 5? 5, do I hear 10? $5 for an NSA sticker. This went for 40 in the morning. 10, do I hear 15? 10, going once, going twice, sold for $10. Thank you. Sorry about that. Thanks.
All right, I'm going to go ahead and get started. I'm going to be talking about context-keyed payload encoding. First, a little bit about myself. My name is Druid, founder of CAU. HD and I co-founded AHA down in Austin about a little over a year ago, and I'm currently employed by Breaking Point Systems doing exploit and attack development. All right, so payload encoders. Basically, what this does is when you're packaging your exploit, you may want to take your shellcode or your payload and encode it so that it goes across the wire in an obfuscated manner. Basically, it encodes the payload prior to packaging, and then it prepends a decoder stub to that payload so that when it's executed at the target, it unobfuscates it and executes the original payload. The decoder stub, like I said, is prepended to the original payload. It executes first, and then it passes execution to the unobfuscated payload. So why would you want to use this? There's a couple of reasons. First, you may want to evade network monitoring detection of things like filtering for common instructions like exec bin shell, add users, interaction with password files, other sensitive files, things like that. Or you may have some constraints on where your payload is going to be traversing on its way to getting executed. So if from your input vector you have say a function like toLower, toUpper, your payload's getting converted to UTF-8, something like that, it might have to go through this restriction. You can use a payload encoder to encode your payload in such a way that it'll pass that restriction without being modified, and then that way it's able to unencode at the target and run your original payload. All right, so there's a lot of examples out there. A lot of good ones are in Metasploit. There's ones that do encoding to alphanumeric, UTF-8. There's some keyed-based encoders that use a key to do XOR obfuscation, things like that. And there's a really cool one called Shikata Ganai, which is a polymorphic XOR additive feedback. The problem here is that the decoder stub's expected functionality is that it's able to decode the obfuscated payload at the target. So all of the existing payloads that, or encoders that I looked at either don't use a key, they use some kind of mathematic way to obfuscate and unobfuscate the payload, or they use a key, but the key is actually included in the decoder stub so that it's able to decode it once it executes. Basically, if you're an observer, watching this type of attack traffic go across the wire, you can capture the payload, and if you want to find out what it's doing, you basically just execute it in a virtual machine or a emulator or something like that, and you can basically decode it for analysis. Most of the ones that I've found suffer from this problem. It's feasible to assume that as processing technology and things get faster and faster, network monitoring devices might be attempting to do this type of thing in a real-time fashion. And the decoder providing all of the information it needs to decode the payload, that would be potentially possible. So how can this improve? Always use a keyed encoder if you can. Also, don't include the key in the decoder stub, which presents the obvious question of, but then how does the decoder actually get the key and perform its job? Which brings me to the subject of my talk, context-keyed payload encoding. Some quick definitions of what I'm going to be talking about. Contextual keying is basically the process of key selection from context information that's either known or reproducible from the target. The context key is the key value which results from that process. The context address is where the context key is going to be located at the target. And a memory map is basically a term I came up with just describe a file containing chunks of static data and their location addresses as we found within an application. So a context key encoder, how is it different from a regular encoder? The encoder itself is pretty much the same. It still performs all the same functions. The difference is in the decoder stub. The decoder stub is basically responsible for not only decoding the original payload, but also locating or generating the context key. All right, so usable context. Basically, I'm going to be talking about a couple of different types of context information that you could potentially use for this. The first one I'm going to talk about is static application data. It's fairly easy to profile if the attacker can reproduce the application's operating environment and execution of the target application. So it's also easy if you have access to the executable, which creates the process that you're going to be exploiting. The context key can basically be chosen from static values found in the process's memory. And you can use things with known locations, static values, the actual application's instructions, things like that. All right, so profiling an application. Basically what you want to do is create a memory map, like I mentioned a minute ago, from one or more methods. Basically you have you can attach to the process, repeatedly pull its memory, throw away things that change, and what you're left with is essentially the unchanging data in the process. You can also parse an application's executable, extract the static sections. You can predict where those things are going to be mapped in memory and store those in your memory map as well. Quick tool I wrote for profiling Linux processes is called SMIMAP. It's on SourceForge right now if you want to go grab it and play around with it. I suggest you get the Subversion copy because it's a little more recent than the packaged version. Basically it relies on proc for maps of memory locations and access to the process's memory. Sometimes maps is a little inaccurate, so it will also do an exhaustive search of all memory if you want to do that, and that takes a little bit longer. Basically, it repeatedly pulls the memory addresses that it's found data at and watches for changes, throws those out. Highlighted is the actual command line to run the tool, and it results in a memory map of the process's memory. So another way to do it, targeting Windows processes, MSFPE scan has been extended to create these memory map dump files. Basically, it targets the application executable DLLs, basically anything that's a PE file format. Again, the command line is highlighted for you, and it results in same type of memory map, and that's included currently in Metasploit trunk. All right, so the memory map I keep talking about, it's fairly simple. It's just a concatenation of a bunch of these data structures. The example here on the screen is for static chunks of data. Some of the other types of data I'm going to talk about, you might need other fields, but you can determine those based on the data type in the file. For static data, we just have the data type, which would be static, the base address of the entire chunk that's stored in the file, the chunk size, and then the chunk data. If you happen to use the O&O hex editor, I've written a template to parse this out. I'll make that available on my website probably early next week, and I'll also include it in the SMIMAP release. All right, so another type of context information you might be able to use is event data. In some cases, the data, you could package that along with your exploit that's going across the wire. If you can predict the location of, say, the process you're exploiting queues up and stores incoming messages and then you exploit it, you might be able to include your key data in one of those previous messages that it caches. Basically, the only real requirement is that the key value that you're looking for at the target is what you expect it to be when your payload gets executed and tries to decode. Another type of context information you might be able to use is temporal data. Basically, this is what inspired me to work on this. I was hoping to find another use for Scape's research in temporal return addresses. His research has a lot of constraints on when the actual data located at these temporal locations is valid, because he was using them for return instructions, things like that. Using it as a context key has a lot fewer constraints. Basically, the temporal addresses are a fairly good fit for purpose for this, and essentially what a temporal address is it's a location in memory where you have some type of a counter. I highly recommend you read that research. It's really interesting. So basically, when you use it as a context key, like I said, there's a lot fewer constraints. The data doesn't, you don't want it to change while you're using it as a context key, and it's viable whenever it's used within its update window, and when it's used as an encoding key and it doesn't produce any bad byte values in your payload. Basically, you just have to be able to predict the value of the temporal data, and obviously frequently changing data is not going to be really useful. If the timer's resolution is more than 1 second, it's going to be changing way too frequently for you to use. But there's a lot of much larger types of temporal data that you can use for that. So a quick case study on temporal data. I'm basically going to use the same one that's in Scape's paper. Within Windows NT, there's a shared user data region of memory. It's always at a known location. That's by design. And it has the system time variable in it, which is basically an 8-byte timer. It's got a 100 nanosecond resolution, and we know what the epoch is. So if you can predict fairly close to the time on the system, you could potentially use this as your key data. As you can see, the different bytes there for that timer are listed out for you and what their update frequency is. Obviously, the first 4 bytes are not going to be very useful. They're under 1 second. They're changing way too fast. But the upper 4 bytes, the shortest of which is 7 minutes, 9 seconds update frequency. If you can predict the system time within 7 minutes, 9 seconds, you can use a 4-byte key. If you only use a 2-byte key, you have to guess within 325 days, roughly. Given the desired length of the key, you have a much larger window of opportunity there. All right, so context key selection. Basically using memory map static data is what I'm going to use as an example. Basically, you select the sequential data at any address that's large enough for your key. You want to make sure that the result of encoding with that key doesn't produce any bad bytes in your payload. Check that the context address itself also does not have any bad bytes in it, because that's actually going to be included in the decoder stub. And then if everything is good, you have your context key and you have your context address. All right, so encoding and decoding with context. Basically, the encoder gets the context key and it works as normal. The decoder stub gets the context address, and it basically, when it runs, it's going to go retrieve the key from that address. So once it's done that, it just decodes as usual because it has the key. All right, so proof of concept. The Shikata-Ganai encoder has been extended to optionally use context keys. From the Metasploit Framework console, this is basically how you would use it. You set up your exploit and payloads as normal. You set the encoder to Shikata-Ganai. You enable context encoding with the variable there. And then you set context information file to your memory map file. That's basically where it's going to go try to attempt to use keys from. And then you run exploit as normal. So a more concrete example, using MS04-007, the Kill Bill exploit against XP Service Pack 0, created a memory map basically using the MSFP scan context map argument. It outputs, it can process multiple files at once, so it outputs into a directory, one map file per input file. And then basically I just took the target executable, loaded it in debugger, noted which DLLs it includes, took all the DLLs and the executable, put them in a directory, ran the MSFP scan on it, created a bunch of map files, and because the map files don't really have any header information, you can just concatenate them all together and make one really big map file. Using Metasploit, you set it up just like I showed you in the last slide, and hopefully I'll be able to demo this for you. Feel free to heckle if it doesn't work. Okay. This is VMware. Over here I have XP SP0, and I don't know if you can read that, but there's this network address. Over here we have Metasploit set up. All right. I don't know if you can read that at all, but I've already set it all up in Metasploit. It's using the correct exploit. It's got the encoder selected, and it's using the map file that I created. Over here, I'm just tailing the Metasploit log file. All right, and I also have Wireshark capturing, but I'm going to do that on my other screen. Okay. All right, so we're going to run the exploit. There's the shell. Over here at the log, I don't know if you can read that at all, but basically down here at the bottom, successfully found context address from the map file. It looks like 76E40045, and the key value, which is going to be at that location. All right, so here's the attack traffic. The badness is over here in the session setup. Which is down here in the security token. All right, so there in the middle is the payload with the encoder, and because it's Shikata-Ganias, the polymorphic one, I don't know exactly where in here the actual instructions are, so I'm going to search for it. This is really hard to read sideways.
Did you turn off random text or whatever so that the A's would get randomized or if you're padding?
No, I didn't. That's just the exploit as packaged by Metasploit. Yeah. This is the Kill Bill exploit from Solar Designer, I believe. All right, so where did my VMware go? Okay, for some reason my VMware isn't coming back up. Okay, there we go. All right, so the address was. Okay. All right, so here's our A1 instruction, which is move address to register. And then here is the context address, 76E40045. So rather than including the key value in the decoder stub, it's actually pulling the key value from memory at the target and then able to decode and give us our shell. So that's pretty much it. I think I've got about 1 minute left, so any quick questions? Yes?
Since a payload generally just sets up like a secure session with the victim, why would anyone care what your payload is?
As I mentioned towards the beginning of the talk, the question was, why would anyone care what the payload is? If you're doing any type of network monitoring, looking for things, you want to filter, bypass filters that are looking for things like execute bin shell, things like that. You want to use a encoder to obfuscate that. Now, as hardware and things like that get faster and faster, I don't know of any network monitoring devices that do this right now, but you could potentially do that in real time. Because the decoder stub has the key in it, you can take that entire chunk off the wire, potentially run it, deobfuscate it, and then look at what's in it and filter it for things like modifying the password, adding users, things like that. Any other questions? Yes?
Does this have any impact on the size of the payload?
Shikata is polymorphic, so it's always changing its decoder stub every time you generate it. I've noticed some slight differences in size, but generally it stays about the same. And because it's using an XOR encoding for encoding the actual payload, the payload itself doesn't change in size. Just prepending the decoder stub obviously makes it a little bit bigger. Anyone else?
What is the overhead of the encoder itself?
That I don't know. I didn't write the encoder. There you go. 27 bytes. All right. Oh, yes.
You encode it to hide intrusion detection. And so, but the key's predictable, right? So could the intrusion detection predict?
Yeah, if my main goal was to prevent the potential of this happening in real time. If you had a person doing forensics on like a PCAP, they could obviously extract it, figure out what's going on, reproduce the environment, profile the target themselves, and find the key information. But obviously it provides a hurdle to doing that. They actually have to go through all of those steps to reproduce the key. And I think that's all the time I have. Any further questions I'll take outside. Okay, thank you.
Real quick, a quick announcement. Our break is starting here in a second.
We still have some ToorCon